So welcome to this session. This session will introduce some key definitions related to what you are going to study on calculus of residues. So the first term of interest is to define what we call simply connected region. So we start by defining what we mean by simply connected region. And a simply connected region is simply, so let's say a region R is called simply connected region if any simple closed curve say gamma, which lies in R, can be shrunk to a point within without leaving the region R. So this is how we define a simply connected region. That a region is called simply connected if any simple closed curve gamma, which lies in this region R, can be shrunk to a point without leaving R. So let's demonstrate on a diagram. If we have this as our X, and this is our Y-axis, and then we draw a circle of radius 2 units. So this is a circle of radius 2 units centered at the origin. This is the motion along this curve. So this region here, region within this circle, what I'm shading, defines a simply connected region, because if you draw a simple closed curve within this region, let's call it gamma, then you can shrink this simple closed curve to a point within the region R. So this shaded part is what I'm calling R, the simply connected region. You can shrink this simply not connected, simply closed curve gamma to a point within this region R without leaving the point, without leaving the region R. Or you can define a simply closed curve as another definition. You can say a connected region is said to be a simply connected region so as a connected region R is said to be a simply connected region if all the interior points of a closed curve gamma drawn in the region R are points of the region R. So with respect to this other way of defining a simply connected region, let's also draw sketches to represent simply connected region. So you can have this. So let's call this one A, this B. So this is the direction. So this curve C2, this curve C1. So let's shade the region. So this is the region R we're talking about. You see, if you draw any curve gamma within this region, then you can shrink this simple closed curve to a point within the region R without leaving the region. So this is a simply connected region. We can also represent another example as so this is the motion. So this arrow is pointing down. So call this one C1, C2, this is C1, this is C3, this is C4, this is C5. So this shaded region is the region R. So this R is also simply connected region, because if you draw any simple closed curve within this shaded region, so call this one gamma, then this gamma can be shrunk to a point without leaving the region R. So those are examples of diagrams representing simply connected region. And so in short, we can say a simply connected region is a region which does not have any holes. It's a region that doesn't have any holes in it. So let's define now what we call multiply connected region. It's our last definition in this session. So multiply connected region. Multi-connected region. So we say that a region that is bounded by more than one curve is called a multiply connected or simply multi-connected region. That is a region which is not simply connected. So let's draw some examples. So for example, if we have this curve and we have another curve here, So let's call this curve C1. This other curve, call it C2. And then this shaded part, or the region defined within these two curves, is what we call a multiply connected region, because if we have a simple closed curve in this region, then there's a possibility of that point being shrunk to a point outside this region defined by these two curves. This is what I'm trying to mean, that this region, shaded region R, is what we are calling the multiply or multi-connected region. So if you draw an arbitrary curve gamma within this region, you see there's a possibility of shrinking gamma to a point which is outside the shaded part. So it will be within this hole or this free space. Another example, we can draw the region between two circles, one of radius 1, another one of radius 2, so this region between these two circles is a multi-connected region, because if you draw a simple closed curve gamma in this region, then there's a possibility of shrinking this curve to a point outside the shaded region. So this is an example of a multi-connected region. Or we can have this is y, this is x, and then we have this curve. Then we can have several other curves. Then we have another one here. Then we have another one here. And then this region So what I'm shading is a multi-connected region, because there's a possibility of drawing a simple closed curve within this region. And when you shrink it, it will be within these holes here. So this is also an example of a region R that is multi-connected. connected. So intuitively, a multi-connected region is a region with one or more pods. A multi-connected region R is a region with one or more pods. And then note that we can convert a multi-connected region into a simply connected region by giving the multi-connected region one or more cuts. Like we say, if you pick this part, then you see this part here will be a simply connected region because there'll be no hole at this point here. And then number two, a function f of z is said to be meromorphic in a region R if it is analytic in the region R except at a finite number of poles. So in the next session, we'll define other related terms, including poles and functions of complex variables. Thank you.